Hi everyone, this is a video for geometry, Math 240 and Math 341, and this is having to do with what are called reptiles. And a reptile is a figure that you can take copies of itself, combine them with no gaps, no overlaps, and you can make a similar figure than the original tile. So a quite famous one, I'm going to do this example with the Sphinx pentagon. So notice this guy here. Oh, first note, I'm drawing it on isometric grid. So isometric grid is a little different. It's not squares, it's equilateral triangles. And the idea is that unlike squares, here you can go to any of the triangle. You can start at any point and go to any of the adjacent points will all be the same distance from it, right? So if I'm starting with the center point, all of these points that surround it are all the same distance from the original one. So you can think of it as a grid of equilateral triangles versus being a grid of squares. But it's nice for a lot of illustrations and that kind of thing. So this is a pentagon because, right, 1, 2, 3, 4, 5 sides. And to think of a tile, you basically think of it as like a cutout. So a tile is basically the pentagon, which is just the points along the edge, plus the interior point. So it's like a solid polygon. Okay. So why is this guy a reptile? Well, I'm going to try to do it. So you take the copies of the original and you try to put them together in a way that, let's see if I can do it. No, right? So it takes a little bit of doing. Maybe I don't do it that way. Maybe what I need to do is, so it's a nice thing to note that, oh, hey, maybe I have to do something like this. Is that gonna work? Trying to think. No. So you keep playing, right? And then eventually, hopefully, you get to realize, okay, how can I do this? Well, you make this like this, and this like this, and this like this, and this like this. Okay, so after a lot of sort of effort, here we go. So that I've taken 4 copies of this guy, the Sphinx pentagon, and I've sort of built, no overlap, no gaps. If I tape these all together, I would get a larger copy than the original. Similar, and notice notice it's flipped from the original, right? The original kind of looked like this guy here, and it's not just blown up, but it's also sort of flipped. But that's okay. It doesn't, if I thought of this as a tile, I could flip it or all that. So I took 4 copies to make a similar figure. Similar figure means all the corresponding angles are the same. So notice all of these angles are 60 degrees. In the original, I've got 60, 60, 60. This angle is 120. And this angle here, here, let me write them. So I've got 60, 60, 60, 120. And this angle here is 60, it's a 60, 60, 60, 60. So it's an angle of 240. Okay, and now in my larger one, the corresponding angles are the same. 60, 60, 60, 120, and 240. So the corresponding angles match up. And now notice the corresponding sides have a 2-to-1 ratio. This side here is, call that length 1. If that's length 1, then this one here, the corresponding side, is twice as long. And the same thing, this guy here, this one here is twice as long. This one here, this is twice as long. The bottom, sort of 1, 2, 3, 4, 5, 6 kind of. And this one here is 1, and then another one twice as long. So all of the sides have a 2-to-1 ratio, and all of the corresponding angles are the same. So that's the definition of similar polygon. And that common ratio is called the linear scale factor. So for this particular reptile, the linear scale factor is 2, because it's a 2-to-1 ratio. Each side, or you think with this one, each side here is twice as long as the corresponding side here. Okay, so and it's kind of cool. It's hard to come up with reptiles that are pentagons. So this is kind of a famous or well-known example. You're going to be exploring this a lot in one of the assignments, and it also leads into a really interesting field of mathematics called fractals. So this is kind of part 1 of some interesting stuff we're going to do later. Okay, thank you.